We'll not do attendance today. I'll just get started. Homework's out. Maybe no one's attempted it yet. That's okay. It'll be due on Friday. Thursday we'll go over the survey results. I love talking about what everyone said, so I won't, of course, name you by name if you have a particularly embarrassing answer, but I might repeat the embarrassing answer anonymously. I've learned lots of good things. For instance, someone last year told me that the green Haribo bears are actually strawberry flavored.
Yes, they are.
Yeah, I learned that. That was a good. So I learned things from these things as well. So I'm hoping you guys have some things to teach me. Okay, so we're done with kind of dealing with numbers. Let's do something with numbers. And so today we're going to talk about our box, and we're going to talk about the box for quite a while actually. But I don't want to start. I don't want to jump right into the box. I kind of want to get us into a position of being able to talk about the box. Right now we just have a box that we're going to fill with a gas or just some atoms. We don't even know if they're a gas. I shouldn't even say that. We won't even make that assumption, but eventually we're going to fill the box full of some particles that effectively are points, right? Like atoms or electrons. We won't do electrons, this get complicated, but an atom, for instance, but we don't have the language to talk about the box yet. So we'll develop that language today and talk a little bit about the kinds of rules and kind of the implications we can make about this box. The first thing I want to talk about is, let's say, for instance, we fill this box up with atoms. Someone name an atom they like. What's our atom of the day today?
Carbon.
Carbon. Carbon's an interesting gas. So here we got a bunch of carbon atoms. We don't know anything about them other than that the box has some carbon atoms. We have a bunch of carbon atoms in there. I'll just put some more in. All right, and what we're going to do is we're going to start to think about the kind of language and the kind of assumptions we can make about this box and see what kind of theory we can build from that. What kind of model for this box we can build. I mean, what we're going to find, of course, if you've taken general chemistry, you might say, okay, well, we have a composite of some number of atoms. We know that they can be in some sort of phase, right? They can be in a gas, they can be a liquid, they can be a solid. We don't know anything about that. And in fact, we don't even know how to predict that. But we will once we get a model for the box and to have a language to talk about the different variables, things that we can measure about the box. So let's do that really quickly. Let's just have a quick brainstorm session. And let's imagine that you're in lab and you're given this box and you're told it has some number of carbon atoms in it. Right? Not told anything other than it's got carbon atoms in it. What are some things we can measure about the box?
Volume.
All right, the volume. That's 2 words. What was that?
Temperature.
All right, so temperature, we'll come back to that.
Pressure.
All right, so we have volume, temperature, pressure.
Weight.
Let's be more specific about weight. What do we mean by weight?
The mass.
The mass of what? Be more specific.
Total.
We get the
Box.
first way the box itself.
Okay, so yeah, so we can say the tear weight of the box. We'll see if that's relevant or not. And we could also measure what's the weight of the mass. Sorry, let me change that. Well, tear weight would be the right term. Let's say the mass of the carbon atoms. What we might find is that the mass is not a particularly useful number to measure the number of carbon atoms. What would be a better number than mass? Moles. Yeah, numbers of atoms. Yeah, so that would, in fact, it's going to be a much better number because, right, the mass of something inside that box is dependent on the constituency, right, or the constituents, right? It's a mass. If you have, let's say, you put 1,000 atoms in there, the mass could be different if it's carbon or if it's helium, but the number of moles is exactly the same, right? Because the number of atoms is constant between those two species, right? So that's useful. What else? What are some other things we can measure? there anything that we can take from these measurements that we've already done and combine them to do something new with them?
Density.
Density, that's a great one. Right, what's density?
Mass divided.
Right, that mass divided by volume. Any others? So there's about 2 more that we could measure.
If you know the temperature and pressure, you probably know the phase.
Well, okay, yeah. So let's put that there. Let's put phase for a second. We're going to find out that that's a little more complicated than you would originally anticipate, but you could probably put that. I'll just write the other ones that we could write, Prince, are the molar mass, right? Right? And maybe that's a better way to measure a mass is the molar mass, right? We know the number of atoms, we know the molar mass, then we can calculate the mass. And the last one is energy. Right? What is the energy of the box? Of course, we don't really have a good way of defining energy at the moment. But you can imagine it's probably important because we'll talk a little, let me mute my phone, excuse me. In fact, the crux of this class is to try to figure out ways to represent the energy of this box, because imagine that we want to manipulate the box, right? Or maybe we want to flow the molecules from one box to another box. The rate at which that happens has to do with the amount of energy stored, because if the gas has very low energy, and you want to flow the atoms out of the box into another one, it's going to take very slow because there's just not enough energy to facilitate that motion. But if the box is very energetic, there's lots of energy in the box, they will flow much more quickly. And of course, we're going to find out that these all relate to each other in some ways too. Now, I want to ask a question about these variables, which is, let's say now that we have an apparatus to measure every single one of these of any box given to us. And let's say we have this box of carbon. We've measured all these things. And then what happens is that I take that box away from you and I give you a different box. Okay? Same atoms. Let's say at the same temperature, right? What changes? What are some things what are these values? What values change as a function of the scale of the box? Let me write that down more carefully. What variables depend on the size of the box?
Volume.
Volume, obviously.
Pressure.
Pressure. Right, so volume depends, pressure depends.
Phase.
As we'll see later, phase will matter.
Energy.
Energy is an interesting one. So before we get to energy, let's see, are there any other ones that don't change with the size of the box on the board?
They do or not?
That don't change.
Not the moles.
The moles, that's right. Or sorry, rather so do the moles change?
The quantity of carbon.
For instance, if you fix the pressure and change the size of the box, the moles are going to change. So moles may change, but molar mass won't. And of course, there's one more that doesn't change, which is the density. Right, the density of the gas or the material inside the box. Right. And then, of course, the rest of them do change with the size of the box. All right, sorry. This is. I'm sorry. I'm confused. I'm sorry. I'm confused myself. I know something seemed weird here. So we're talking about things that depend on the size of the box. Right. We have volume. So pressure does. Let's talk about pressure for a second. All right. So we're talking about things that dependent on the scale of the box. So volume certainly depends on the size of the box because it measures the size of the box. Of course, if we divide the system by the size by 2, then we have the mass. So the mass changes, of course, of the box. If we have the size of the box, then obviously the moles change. And it turns out if you have the size of the box, you also reduce the energy. So energy depends on mass, on the size of the box. And we'll see that very clearly once we start talking more about energy. right? And so the other ones that don't are pressure. And the reason why pressure doesn't depend on the box is because pressure will be a function of the number of molecules inside the box and the temperature. So if those are fixed, then pressure doesn't change based on the size of the box. Of course, if we have the box, the temperature doesn't change because the temperature has nothing to do with the size of the box. Molar mass does not change, of course, because that's a fixed quantity. And of course, the density, it doesn't change at fixed temperature. Right, so we have some things that depend on the size of the box and things that don't depend on the size of the box. And we're going to find that these are very nice things to measure, pressure, temperature, and density in particular, because they don't really matter on what the box looks like. They only matter, say, on the material that we're looking at, the temperature we're looking at, and basically the number of molecules in the box, which is the pressure at a fixed volume. Okay. Now, there's something I want to look at, which is very interesting, in that temperature and energy are on two different sides of this. Of course, when we talk about a temperature, we think about energy, right? We think about the energy of atoms moving around the box, right? And we'll show that that's what that means. But notice that temperature does not depend on is what we call a size. Let me write that down. This is a size-intensive property, which means it's independent of the scale of the system. And these are size-extensive properties. Right, so we have two things that we can measure about energy, temperature and energy, total energy and temperature, but they have completely different size properties, scale properties. Temperature in some ways is a scale invariant measure of energy, and we'll see that. But energy can be of many different things. So it turns out that you can have the same temperature, but your energy can be very different. Because, for instance, as you start to make the box smaller, you might increase the potential energy of your system, but you won't see that in the temperature because that's energy stored within the atoms themselves. Okay, and that's very interesting that we can measure energy potentially by using temperature because temperature has nothing to do with size, right? Any system, if you can measure a temperature, then the system is in similar energetic similar energy as a box that's a different size that has the same temperature, right? It's similar physics. All right, and I want to tie this in because this gives us our first law. All right, so let's go ahead and erase this for now. So for the next couple of lectures, we're going to be talking about the so-called laws of thermodynamics, which are going to be a set of 4 laws. Even though there are 3, there's technically 4. You often read there are 3 laws, but I like to think there are 4. And they're kind of like Newton's laws, but for energy. Okay, and they'll help us define what energy is, how do we measure it, what is a measurable energy, what are the minimum amount of energy a system can have. There will be a number of different things that we can get from these very simple laws that allow us to start building a model for this box of gas or whatever material we have. And so last year, I kind of introduced them all at once, but instead I don't want to spoil it, so we're just going to kind of go one by one and talk about them and introduce them as we go. I think it's probably easier to talk a little bit about them separately first. So let me make sure I have my Zeroth Law. Yeah, so the first law is aptly called the Zeroth Law of thermodynamics. And this allows us, this law in some ways gives us a character, so what's the word I'm looking for? It gives us a restriction, if you will, on when temperature is a meaningful number. When is temperature defined? Is actually maybe a better way to think of it. When is a temperature defined? When is it a defined thing? And it's a very simple argument. Imagine you have different systems. Okay, imagine you have different boxes. Okay, A, B, and C. So if you have, so let me write that. Often when we talk about a system, we talk about a closed environment, maybe like this, like a box of gas. Right? We'll have many different systems, but this is the simplest system of them all, just a box with some stuff inside of it at some temperature. And the Zeroth Law says something very simple. The system A is in what's called so-called thermal equilibrium. We'll talk about what that means in a second. With system B. And system B is in thermal equilibrium with system C. Then system A is in thermal equilibrium with system C. So this is what we call the syllogism law. If A then B and B then C, then A then C. A syllogism from logic. This seems trivial, right? If we can associate some connection between A and B and a connection between B and C, then there's going to be a connection between A and C. It turns out that this gives us a reason to believe temperature, that temperature is a well-defined thing. And the key for that is this idea of thermal equilibrium. And so everything in this class is going to be in what's called so-called thermal equilibrium. All right? We're always going to talk about things in equilibrium. And the reason why, as we'll find out, is that thermal equilibrium means that you can define a temperature for a system. If a system's not in thermal equilibrium, it doesn't have a well-defined temperature. And if it is, it does. And I'll explain what that means in the context of the Zeroth Law in just a second, once we talk about what thermal equilibrium means. So I have a very nice definition of what thermal equilibrium is, and we'll give an example with our box in a second. All right, so I'm going to write definition here, thermal equilibrium. Okay, so a system's in thermal equilibrium if and only if its temperature as a function of space, I'll explain what I mean by that in a second, is constant in time. Basically, the temperature is unchanging over time. Okay, that's one way to describe it. Another way to define it, which will be useful for us once we start talking more about energy, is that there is no net flow of energy or net change in energy across the system. Let me explain what I mean by that. Let's, for instance, imagine we have this really cool thermometer, all right, that we can stick in our box. So let me draw it with paint. Imagine we put a thermometer here, a thermocouple as we call it, and we want to measure the temperature at this point, T of X, Y, Z, right? All right, so we measure temperature there. Right? We stick it in, and now we put one over here. One right there, and maybe we'll put one right there. Right? We'll measure it at every different point in space. And the system, this box is in thermal equilibrium if we read the same temperature at every point. Okay, assuming that this box is isolated from everything, right? That it's not exchanging heat with the outside. You know, it's completely isolated. It's as if it's its own internal universe that's sealed off into a giant box. This system is only in thermal equilibrium if the temperature is the same at every point. Okay? So that's what I mean when I mean thermal equilibrium, is that if we allow this box to sit here like this, We measure the temperature, we go eat lunch, we come back, we measure the same temperature, we go out, for a year or 10 million years and come back, the temperature is exactly the same. Right? That means the system's in thermal equilibrium, which means it's kind of equilibrated into kind of I keep using the word equilibrium, excuse me, I don't want to be circular. But it's just like it's set into like a nice minimum energy position. Everything's kind of normal and chill, and there's not really any need for molecules to move from one direction to the other. Everything's kind of like uniform. And so we're going to be talking about uniform systems, right? And what I mean by uniform systems are systems where the temperature doesn't change in time. Okay. However, we may want to consider systems that do change in time with temperature. For instance, let's take this box. Like what happens if we do this? Here's our box. I'm just going to cut it off the side. And then what I'm going to do is I'm going to put a wall in the middle. All right, so we have A and we have B. All right, we've put a wall in the middle. That can't exchange anything, so this is a fixed wall. It's an impermeable wall, insulated wall. Okay, and what I'm going to do now is I'm going to chill B to 77 Kelvin with liquid nitrogen. All right. So what I'm going to do is I'm going to stick a liquid nitrogen cooler around the box section B. I'm going to let it cool down to 77 Kelvin until the entire box reaches 77 Kelvin. And we're going to let the temperature of A just be room temperature. Okay, and now what I've done is I've waited long enough for all this to equilibrate. Now my question to you is this system in thermal equilibrium? It's an interesting question. Nothing can exchange across the wall. I'm sorry, what was the answer?
Yes.
Yes, that's correct.
Two separate boxes.
Right, they're two separate boxes, exactly. Nothing can exchange between the two walls because, well, again, nothing can change, right? So these are both equilibrated separately. And in fact, what this is two systems both at equilibrium with each other, right? So the Zeroth Law doesn't apply here because there's no way to exchange heat or exchange temperature or however you want to think about it between A and B because there's a wall. Right? So now what's going to happen is I'm going to change this wall. I'm going to still have a wall. I don't know how to draw this. I'm going to draw it like this. That's not really a good way to draw it, I think. Now I'm going to allow a wall that allows transfer of heat, but not atoms. Okay, so atoms can't move from A to B, right? So the moles in A and the moles in B are fixed. But this idea, this concept, we haven't talked about heat yet, but you can imagine heat if you think about this as your air-conditioned room, and this is the hot outside, and you open the window. But you have a fine mesh where so atoms can't exchange, but heat can exchange. What happens?
They do system temperatures now.
I'm sorry, say that a little louder.
There's a new system temperature.
Right, right. And so the way that's going to happen now is heat's going to exchange. And so the temperature is going to drop, and the temperature here is going to rise. This system's not in thermal equilibrium as this happens, though. Right? This is the system equilibrating to a final temperature. Right? Because if we measure the temperature at any point across time, it's going to be changing, right? Because this is slowly going down in time, and this is slowly increasing in time. But eventually we can go to lunch and come back, and what we're going to find, if the amount of material in the boxes are the same, right? The number of moles in A is the number of moles in B, everything's the same except for the temperature, then what we're going to find is that the temperature on both sides is the same. And so the new temperature, they're both at T new, if everything's equal, will be 298, the average of the two temperatures, divided by 2, whatever that number is. 300, it's like 150 something, right? It's like 150 Kelvin, give or take. Right? And now this system's in thermal equilibrium because now everything's equilibrated to a new temperature. The temperature is exactly the same across both of the boxes. And so we can now say that A is in thermal equilibrium with B, and that we have a well-defined temperature for this system. Right? And so what we're going to do is when we think about processes, things like chemical reactions or transport, moving something from one spot to another through diffusion or convection or anything like that. So we're going to be thinking about differences in temperature and watching temperature and mass flow in order to reestablish an equilibrium. And ultimately, the physics that we look at are only going to be at an equilibrium, a thermal equilibrium. Imagine watching the heat flow from here to here. That's a very, very difficult concept. But as we're going to find out, that the physics of that are immaterial. It doesn't really matter how heat flows from A to B. The only thing that matters is the starting point and the end point. And we'll be able to prove that soon. So we can sit here and say, well, as heat moves from A to B, there must be some sort of complicated motion of heat being transferred. There's collisions going on. I mean, the heat has to go across in some very complex way. And we could talk about the physics of all of those things. But what we're going to find is that the end result, the net change, which is this, is the same no matter what happens microscopically in between. The only thing that matters is the beginning and the end point. And let me write this down. We're going to return to this very soon. And this is a really interesting point, just to keep in the back of your mind, because when we talk about enthalpy and entropy, which we'll talk about in about a week or two, we're going to see this term come up a lot. It's about what are called state functions. Functions whose, let me think about it this way. It said, let's think about state functions as variables whose effect on a system depend only on the beginning and the end points. And just to go back to just to reiterate this, that what I mean by that is that the only thing we need to know about how to predict what happens to the box when we allow heat to exchange is to know the initial point and to know the final point. And that's all that matters. Everything that we can calculate in thermodynamics only depends on these. It doesn't depend on anything that happens in the middle. Imagine, for instance, imagine that we could represent heat as a ball, right? Like as a particle, which is not very fair, but just imagine that. And we want to move this heat ball from here to here. Well, there are many different ways it can do it. One, it can go through a straight line. One, it can go through a loop-de-loop. One, it could draw that S that all the grade school kids do that I can't draw, the crazy S with the, anyway, I'm just being stupid now. Right, it can do all these different paths, right? And of course you would say, well, that's a problem because maybe the physics are different if it goes through a loop-de-loop or it goes through a straight line. But it turns out that it doesn't. It turns out the only thing that matters is the beginning point and the end point. And we can calculate everything about the physics of this system just knowing these two things. Right? And it turns out that the reason why is very subtle, with this idea of a state function. And there are going to be things that we can measure about our system that aren't state functions, and we'll be able to manipulate them to turn them into state functions. So we don't have to worry about the path that things take from point A to point B. We only have to care about point A and point B. Okay, and that's going to be really, really powerful because it's going to make things really easy to do. Right? We don't have to worry about complicated physics because all of that cancels out. It only matters about the beginning point and the end point. So back to this idea of Zeroth Law. Right, the Zeroth Law guarantees that we can use temperature to measure something, and that temperature only means something when the system is in thermal equilibrium. And the idea is to just stick the third body here as a thermometer. And And now I'll ask the question for the zeroth law. Is A in thermal equilibrium with B? Let me put the thermometer up here too. Let's start at the beginning. There's our thermometer. Let's start at the beginning. Is A in thermal equilibrium with B? No. Is B in thermal equilibrium with C? Maybe, right? B probably measures C because they've been sitting together for a long time. But that means A is not in thermal equilibrium with C because A is not in thermal equilibrium with B. So that means that the temperature that we measure in C is not defined for A, and so the entire system doesn't have a defined temperature because the temperature varies across the system. But down here, we have thermal equilibrium between A and B. They're at the same temperature. And of course, C is equilibrated to them. So A is in equilibrium with B, B is in equilibrium with C, so A is in equilibrium with C. Right? All this says is that thermometers measure temperature of systems in thermal equilibrium. Right? Now, again, you might imagine that real boxes with partitions between them can also move mass, right? So right here, this magical wall we have only transfers heat but not atoms. Right? That would be like a metal wall, something that's conductive to heat, something like aluminum. But imagine that it's a fine mesh instead, right, that allows atoms to pass through. Well, the atoms actually have crazy trajectories, right? In fact, what we're going to find out is that atoms in a gas move randomly. So there's a probability that the atom will just move straight through, and there's also a probability that it's going to do loop-de-loops all over the place before it transfers over. But thankfully, as we'll find out, the thermodynamics tracks this for us. We can use these state functions to track mass flow of mass from one system to another, and they're state functions. So that means we only care about the initial point and the end point. We don't have to worry about all the loop-de-loops and all the complexity in the middle. We only have to worry, the only thing our calculations depend on is the beginning and the end point. Questions? Okay. Great, so that's the zeroth law. Right, that thermometers work, and that if you measure two different points in a system and you get different temperatures, then your system's not in thermal equilibrium. Okay, so you can't define it as a single system. That's good, because otherwise we'd be in a bad situation, and we wouldn't be able to measure anything. Okay. So now we're all good. So we have a thermometer, we can measure temperature, right? And we know kind of intuitively that temperature gives us a measure of energy. So let's talk a little bit about that. Before we really define what temperature is, let's think about our system now. Let's take each of these particles in our system, in our box, and let's let them move around a little bit, okay? So again, these are just balls. They're just spheres. They don't have any, actually they don't have any shape necessarily. Let me see, where's my ideal gas stuff? Yeah. Must be here. Yes. So let's talk a little bit about this box of gas and talk about the gas itself. All right, and what we're going to do now is define kind of some simple rules about our atoms inside of our box, right? So now we're going to have to start talking about, well, if there's some energy, how does the energy being shown? And of course, the way that energy in a box of gas is going to be represented is because of velocity and motion of the atoms in different directions. Right, you can imagine that these atoms are bouncing around in this box with some velocity, v. Okay, and so what we want to see is how does this motion, this random motion of all these atoms, correlate to temperature, right? How are they associated with each other? And it's going to take us a little bit to get to that point, but we will. And what we'll find is that temperature tells us something about the internal motion of these gas particles. But in order to make things simple, we need to make some assumptions. And, unfortunately, I kind of said at the beginning of this class that we're here to not make assumptions about things, but we're going to cheat. we're going to do the physics way of not making assumptions, which is we're going to make assumptions, and then we're going to correct for the errors that our assumptions generate. Okay, so we're gonna do our due diligence, but we're going to kind of split it up a little bit. We're going to solve an easy problem first, and then we're going to correct for the real problem by including the corrections of small changes in the easy problem. Okay, and this is what physicists do all the time. Physicists will come across a complex problem, and they'll say, "Well, geez, that's a hard problem. Well, what's the easiest way I can simplify it to solve it?" And then they figure out the differences afterwards. Right? And that's what we're going to do today. So what I'm going to define today is our gas inside of this box. So we're going to make some assumptions about our gas. We'll say our material. And these assumptions are the ideal gas approximation. And there are a few assumptions that we make about ideal gases. One is that each particle is point-like, which means it has no physical shape. It's just a point, like an electron, of mass, and has mass m, some mass. We'll just call it m. Right. M is 12 AMU if it's carbon. All right. We're not going to worry about whether the atom has a radius, right, or a diameter. If it's a sphere, we'll worry about that later. Right. That's one of the things we can correct for. Each element is non-interacting. Each particle is non-interacting, which means they don't attract each other or repel each other. No attractions, no repulsions. Okay? Obviously, that's not true. We know atoms dip, well, for instance, you have a negative charge and positive charge, they attract, obviously, but it turns out any atom is attracted to another atom. We're just going to ignore that for now. We'll correct for it, as always. Another interesting one is that we're going to say each particle moves randomly. In agreement with Newton's laws of motion. Right, each of these particles is, as physicists call it, spherical cows. They're just spherical cows floating in a nothingness. It turns out that that's probably a good assumption to make. If we break this assumption, then all hell breaks loose. And that's a really scary place to be, so we're not going to break that yet. If we assume that the particles move in not random positions and that they don't move in Newtonian way, things get complicated. If you've ever mixed, cornstarch and, what's the other thing you mix with cornstarch to make that stuff? Water, cornstarch and water, right? If you think about that, if you heat that up real high to when it's a very viscous liquid, it does not move in Newtonian ways. And the physics of cornstarch and water is just brutal, right? It's very scary. So we're not going to worry about those things right now. We're going to assume everything works in Newtonian laws. And then we're going to say that each particle collides elastically. I'll explain what that means in a second. With each other and the walls. Right? They can hit each other, but they can't exchange energy. And I'll just write that elastic means no energy transfer. They just bounce like balls, like pool balls. So when they collide, they don't release sound wave, pressure waves, like sound or anything like that. They just bounce off each other, like they don't know they exist. Okay, these are enough rules. These are enough assumptions for us to actually make a full-formed theory about this gas. Okay, and what we're going to find is that these actually work pretty well, except at certain limits where certain parts of the ideal gas approximation break down, and we're going to have to make corrections for those when we need them. All right, we'll eventually get to a more universal method for modeling a gas in a box, but for the time being, this is appropriate. The changes, the corrections, if you will, are only a small fraction of a percent. to the predictions that you get from a fraction of a percent to the predictions that you would get from these assumptions. Okay. Now what we're going to be able to do is think about the energy of this box as kind of an average energy of all the particles, right? And what this means is that if the particles move randomly in accordance to the motion of law, there's no attraction forces, there's no potential energy, there's just kinetic forces, that the energy of a particle is just kinetic energy. There's no potential forces. And a particle would be 1/2 mv squared. Right? So every particle has 1/2 mv squared energy, where the velocity is random. Because some particles might not be moving at all, some might be moving very quickly, some might be moving in an intermediate way, because they're moving randomly, right? So because they're moving randomly, that means that the average energy of the system has to be like an average, right? It has to be a mean quantity, because some particles are going to have a ton of energy, and some particles are going to have no energy at all. They're going to have a distribution of energies or velocities, if you will, because they're random, right? It has a distribution, like a bell curve. And so that means that if we were to measure the average energy of the box, then that must mean that we're measuring the energy of the box, we're actually measuring some average energy of all the particles together, where some are faster than others, and some are slower. Okay, and so I want to break this down before we kind of dive into the math here to get to the ideal gas approximation. I kind of want to illustrate this point about randomness. And the way we're going to do is very simple. Let's let our box contain just a few atoms. A few atoms. So let's say a few atoms. Let's say 5. Okay, and then let's fix the energy of the box. Fix the energy of the system. It's some number. Let's let the number be called U. Okay? And then we say that the energy, right, and then we apply the ideal gas approximation. And assume that the kinetic energy of one of the 5 particles, atoms, is an integer, whole number. All right, we're just going to work with integers for now. So it can have a kinetic energy of 1, 0. It's a positive number, of course, because of v squared. Right, so you can have, there could be ones that have energy 0, energy 1, energy 2, energy 3, and so on and so forth. Okay, we're just going to keep it simple. Okay, so let's for instance fix our energy to be 1 unit. Okay, so we have 5 atoms and only 1 unit of energy to distribute between them. So I'm going to draw a table here. 1, 2, 3, 4, and 5. This is our atom number. And then we can come up with the different combinations of energy for each particle such that the total energy is 1. For example, imagine that we had 1 unit of energy for atom 1. Total energy is 1, so that means we've used all our energy, so that must mean that these are 0. The total energy is the sum across the row. Right? So 1 plus 4 zeros is 1. Everything's good. Right? How many other combinations are there of energy 1? All right, let's do the next one. What would that look like?
0, 1, 0, 0.
Right. Right, there are 5. Right, we can do this all day. So interestingly, and there's one more. Right. There are only 5 arrangements of these 5 atoms that satisfy everything about our system. Right? Okay, so what happens now if we set the energy to 2? Well, we're going to have all the combinations where a pair have u equals 1, right? So 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and, and so on and so forth. And 5 combinations where one particle has energy 2. Right? So this is 5 combinations. And we can count how many this other one is. That's 5 plus 1 and 2, 1 and 3, 1 and 4, 1 and 5. That's 4. 4 plus 3 plus 2 plus 1. 4 plus 6, 7, 10. So 15 roughly, or about 15 combinations. And just now, let's just extrapolate, right? What happens if we set u equals 100? Well, there are tons of combinations, right? I mean, it's more than we can count, right? A massive amount. Now, when we go, what's going to happen? What this means is that every time we make an observation of our system, imagine that we had a box that allows us to pull every atom out and ask how much energy each one has, right? When we do that, remember they're moving randomly, so every time we do that, we're going to get one of these 5 combinations, right? If we're satisfying u equals total energy V1, and there are 5 atoms, then 20% of the time we're going to get one of these choices. Right? So there's a statistical probability about it. Notice how this row is exactly the same as this row, because there's nothing different between carbon atom 1 and carbon atom 2. Right? So these are all the same arrangement. It's just that different atoms, different carbon atoms have different energies, but in fact the system has the same energy, everything's exactly the same, you just have 5 different copies. Okay, and then, but something happens when you have u equals 2, you're going to have all these copies where you have a pair that has u equals 1, energy equals 1, and then you have some combinations where one particle is equal to 2. So you have different combinations of different energies. And you can figure out the probability, and because it's random, you can figure out the probability of finding a system in one of these conformations based on the number of arrangements that have that energy or that state that you want. Right? So no matter if u equals 1, we always have a 20% chance of grabbing one of these arrangements. But notice if u equals 2, when we check the system, there might be a chance where 2 particles have energy, and there might be a chance where only 1 particle has energy. Right, so there's this statistical variation that occurs, right? There's this statistical randomness with our gas. And you can see that very clearly. Now notice that we've only used 5 atoms here. It's a very, very, very small number of atoms. Right? But when you get to 10 to the 23 atoms, when you get to a mole, you can imagine this calculation becomes impossible. But it doesn't matter because the statistics are exactly the same. There's some probability of being able to identify one of these combinations, and a system at a given amount of energy is going to be a statistical distribution of all of those possible combinations. Right? So energy of 1, you only have 5 different combinations. Energy of 2, you have 15. U equals 100, you have millions or billions of combinations. Right? So every time you look at your system, you're going to get one of them out. But realize that the system is constantly moving, constantly average, so in fact, every time we measure, we're going to get a random answer, right? There's no way to actually pull out one of these combinations. You're just going to get one at random. Same here, and same here. Everything's random. So there must be some sort of formula for us to understand the probability of finding a system at a particular energy. Okay, so we're never going to be able to fix the energy to 1 or 2. Right? We're never going to be able to do that. It's impossible. So, but instead what we can do is we can set our system to some average energy and calculate the probability of finding the system in a particular arrangement of velocities that satisfies the statistics at a given kind of average energy. The average energy we're going to use is temperature. Average kinetic energy of our system is going to be proportional to temperature. Right, we know that, right? If you heat something up, it has more energy, right? We know that just intuitively. We know that temperature measures average energy in some ways. But notice that the units are different, right? So we have energy, average energy, we'll say, which is with bars, mean energy, if you will, is proportional to temperature, but the units disagree because the units, of course, here on this side are Kelvin, and the units here are on this side are joules. Right, so it turns out that there's a proportionality constant. To convert between joules and energy. A proportionality constant between joules and Kelvin. Right, what is that unit? What is that number that converts energies, average kinetic energies, into temperatures? And it turns out that if you measure E in units of joules per mole, okay, you can convert this into temperature, average temperature, by multiplying by the gas constant R times temperature. This is what's called the ideal gas constant. And of course it has units of joules per mole per Kelvin. Right? If you multiply R by T, you multiply Kelvin by 1 over Kelvin, you get joules per mole out. If you divide E by R, you get Kelvin out. Okay? And the units for I'll just write it down because we'll see this constant a lot. Let me find it real quick. Here it is. I'm sure you've seen this number before, 8.314510 joules per Kelvin per mole. All right, this is really neat. This tells us exactly how much energy is in a unit of temperature. Right, if you have for an ideal gas. Right, so if you have an ideal gas and you raise the temperature by 1 Kelvin, that means you've increased the energy, the average kinetic energy of the system by 8.314 joules. Right? It's just a conversion between temperature and energy. The important thing is that this conversion only works at thermal equilibrium. Right? Because temperature measure, right? If we don't have a fixed temperature, then there might be portions of our box where the energy's higher, average energy's higher, and there are portions of our box where the energy's lower. And so when you measure a temperature of 1, you don't know anything about at one spot, you don't know anything about the temperature or the energy at a different spot, so the conversion might be different. Right? But for an ideal gas at equilibrium, every unit of Kelvin gives us an extra 8.3 joules per mole in kinetic energy. Per mole. That's actually a really, really small amount of energy, right? Because this is the amount of energy pumped into 6 times 10 to the 23 atoms, right? Which is not very many, or is a lot. So there's a different number that we use. So this is the ideal gas constant, and the constant we often see is what's called Boltzmann's constant. Which is notated K sub B for Boltzmann K. I don't know why the K, but it's K sub B. And that's Avogadro's number. That's the gas constant divided by Avogadro's number. It's the amount of joules that you get per unit Kelvin per molecule or per atom. And that unit, of course, that number is very small. I don't remember it off the top of my head, so I'll just write it down. 1.380658 times 10 to the 23 minus 23 joules per Kelvin. Okay, so for every Kelvin you increase the temperature, the average kinetic energy of an ideal gas atom increases by this much energy, right? So this kind of this encodes all the information we need to know about the average kinetic system, energy of a system, and put it into a size-intensive variable, temperature, right, which is independent of the scale of the system. Right? And it tells us something about the amount of thermal energy or the amount of kinetic energy our ideal gas has at any given temperature. Okay, so we're going to interconvert between these numbers. Sometimes we're going to do things in terms of single molecules using Boltzmann's constant. And sometimes we're going to use the gas constant because we're going to talk about moles of gas. They're the same number, but they just one's for molar and one's for not molar. Okay, any questions so far? Okay. I want to get to a final point about all this, right? Because I've talked about this idea that as you increase the amount of energy in a system, the combinations of energy that go into each atom increases dramatically, increases exponentially, right? We went from 5 to 15 to, at 100 we're at something like, geez, I don't know. It must be something on the order of 10 to the 30, or something like that. It's a very large, it's probably more combinations than there are atoms in the universe at this point. And so that's, of course, this is a completely useless thing for us to deal with because we're never going to be able to look at, lists of 10 to the 30 different numbers. So we need to think of a way to do statistics that allows us to calculate the fraction of a system being in a specific state as a function of the temperature. Okay? And there's a really, really easy derivation that gives us a formula that's super useful. And I have to pull it out of this book because this is actually a new idea that I hadn't thought about, and I forgot to write notes down. I'll make sure to send a copy of this chapter out as well so you can read it. I just want to make sure I get the math right. Yeah. Right. So let's say again, each of these rows is what we call a state. Right? Our system is this big box, and the system can be in different types of states, and each of these rows correspond to a state of our system. Okay? So let's imagine that we have in our system, there exist two states. There are many states, but let's point two states. There exist two states, A1 and A2. All right, let's say, for instance, I don't know, this could be A1 and this could be A2, for instance, right? It doesn't matter. Just any combination of energies into atoms. Okay. So now I want to ask the question, what's the ratio of states 2 over 1? How much more likely is it for the state system to be in a state 2 than it is in state 1? Maybe a better way to look at it is that combinations where there are a pair of U equals 1 is A1, and combinations where there's a single molecule of energy 2 is A2, right? Something like that. Doesn't matter. And let's imagine, right, this must be a function of the energy, right? Again, the proportion of states that have higher energy are going to be more likely if your temperature is higher or your energy is higher. And let's say, for instance, that state A1, sorry, I just want to write one more thing. State A1 has energy E1, and state A2 has energy E2. Again, don't worry about the numbers so much. Just, we showed that there are states, they have energies. There are different arrangements of the atoms, different velocities, they have different energies. Okay? Don't have to be any more specific than that. But what we can say is that the ratio of things, of states in 2, the number of states in 2 versus the number of states in 1, is probably going to be a function of the energies of those two states. Given, right, if the higher the energy may be at a given temperature, the lower probability we're going to be able to see the system in one of those higher energy states. We can simplify this a little bit because we know, so energy in this case, let's rescale the energies. So E1 is 0, so E1 prime we'll say, and E2 prime is E1 minus E2. All right, so we're just going to change it so that the base level for the state 1 has energy 0 and everything's relative to it. Right? We're just changing it to a relative energy scale. Okay, what this means then is that A2 over A1 is just a function of the energy difference. Like that. All right, we don't need to worry about what the function looks like yet, but we know that it's probably a function that has to be a function of the difference in the energies. But now let's apply the Zeroth Law, right, and assume that the whole system's in equilibrium, which would mean that a new state A3 divided by A2 is still just that same function, but now it's the difference in energy between E2 and E3. And we can also write for A3 over A1 is the same thing. Right? That's what the Zeroth Law tells us, right? That if this rule applies to two states, applies to another set of two states, and applies to all of them together. So now what we have is that these must be true. These equations must be true for any three states. Right, and we can write now A3 over A1, doing some algebra, as A2 over A1 times A3 over A2. Right, which means that A3 over A1 is just f of E2 minus E3. That's this equation at the top, times f of E1 minus E3. Okay, so when you skip states, if you will, you just get products of the function. So what that means now, and of course the other side of this, this is f of A1 minus A3, E1 minus E3. I'll rewrite this just a sec. So what we have is f of E1 minus E3. That difference is equal to a product f of E2 minus E3, f of E1 minus E3. Did I get that wrong? Oh, sorry. This is a bad typo on my part. 2 minus 3, excuse me. And A2 over A. Okay, I just have bad writing everywhere here. So 2 and 3 and 1 and 2. Yeah, 2 and 3 and 1 and 2. Excuse me.
Yeah.
Right. Okay, so we have some function that satisfies this. And it's really interesting. Another way to write this is that you have a function of x plus y equals f of x times f of y. There's only one function that satisfies this expression. E to the x plus y equals e to the x times e to the y. Right? It's an exponent. So what that means is that the fraction, the function e, must be e to some number, I'll call it beta, times e. Or beta is some number, some proportionality constant. So what that means is that the probability of the ratio of states 2 divided by the ratio of states 1, the ratio of states 2 to the ratio of 1, must be E, once you just do a little bit of algebra, beta E1 minus E2. It's beta times the energy difference. So you could say in general that some state m, or some state n divided by some state m, the ratio of n states n over the states m, is e to the minus b beta em minus en. Which means that that one of the states, basically the amount of states of J, state, just any old state, has to be equal to, or let's say proportional to, e to the minus beta ej. What this means then, so I'm going to go ahead and erase all this. This is a beautiful formula. I mean, we've taken something now, is that the probability of finding a system in a given state of energy E. Okay? We'll call that the probability of E, P of E. P of E is proportional to e to the minus beta times the energy of that state. Now, I'm not going to do all the math yet, but what we haven't defined yet is this beta. We don't know what this beta is, right? But you can do a little bit of math, and what you find is that beta is 1 over kBT. 1 over Boltzmann constant times temperature. Right? These have units of inverted joules. Right? So you have a function of energy, which is in joules, times 1 over joules. So you have a unitless number overall. Bless you. So that means that the probability of finding a state at energy E is e to the minus E over kBT. All right, let's not equals. Let's not do equals yet. We're not there yet. Proportional to. We'll have to talk a little bit about the equal sign in next class. I want to highlight this because this is very powerful. What this tells you is that if we want to look at our box of gas and we want to ask the question, what's the chance of us finding it in a particular orientation or state? All we have to do is calculate the energy of that state and divide it by the temperature, the thermal energy of the system, kT. Right? And the probability of finding that state, the probability that it exists in your system, is e to the minus E over kT. So what that means is that as energy increases, fixing temperature, the probability goes down. Right? The higher, the lower, if the temperature is fixed, the higher the energy, the probability decreases because it's e to the minus that. But if you fix the energy, increase the temperature, the probability goes up because you have more thermal energy to use, the system to use. Thermal energy is more thermal energy available, so there's more likely probability of finding the system at some energy E. All right, this is called the Boltzmann distribution. With just this formula, and just a little bit of work, which we'll do next class, Boltzmann's distribution, we can calculate all of thermodynamics. All of thermodynamics. Yes, question?
For the e to the negative energy,
Yeah.
is KB is T with KB, or
Yes.
is it times that whole?
It's beta, which is 1 over K times T. So it's the product of K and T together. So actually this is a really good hint to tell you guys just to kind of keep it easy. Whenever we talk about temperature, if you ever want to discuss the energy content at a given temperature, you can always say that let's call it EC. EC is proportional to Boltzmann's constant times temperature. All right, so anytime you talk about temperature, you can always multiply it by Boltzmann's constant or gas constant if you're doing it in moles, or you can also write this in, so this is in joules, or in joules per mole. RT. Right? You're always going to multiply temperature by R or KB, depending on which units you're using, and that will always give you an energy back. And it turns out that the total thermal energy of a system, the energy that the system has just because it has a defined temperature, is always proportional to KT. All right, well, sometimes there's numbers on the outside, like 1/2, 3/2. We'll get to those later. But in general, if you imagine that you have a process that takes X amount of energy to do, right? For instance, when we talk about reactions, they're going to have what's called an activation barrier. There's this hump in energy you have to get over for the reaction to go. And if you know that, you can kind of roughly get a sense of what temperature you need to be at, because if the amount of energy is E, then you know you need to be at KT energy in order to accomplish that. So K always sets the scale for energy with temperature. So if you have something that is, so this is roughly 8.3 times Kelvin. So if you have something that's like a kilojoule per mole, then the minimum temperature you're probably going to need to be on average above that energy is going to be 1,000 divided by 125 Kelvin. Right? So 1 kilojoule per mole is roughly 125 Kelvin, for instance. So of course, many reactions have barriers of many kilojoules per mole. And of course, in order to get over those barriers, sometimes you have to be at very high temperatures, right? Which is why we reflux things at 100 Celsius, so we can get over these barriers easily. Right? And so so you can always interconvert between energy and temperature this way. You always have K and R, and you can talk about either one, but you always have to make sure that you always have this proportionality constant there to convert between the two. Does that answer your question, Megan?
Yes.
Good. Okay. Any other questions? Okay. So, yeah, in the back.
Would we need to know how to apply the Zeroth Law like you did for all that to find the Boltzmann distribution, or is that just to show the link?
Just to show the link.
Okay.
Yes, just to show the link. We're not gonna use this equation too much in this class, but I want to talk about what we're gonna do is we're gonna take this equation and we're going to apply it to this system, this box of gas, where each of the states of the energy, each state of the system, are some combinations of velocities of our atoms, and we'll be able to calculate an equation, which is the ideal gas law, by starting here. Right? So this will get us to the ideal gas law, and that's ultimately what we want to get to. So this is just kind of some theoretical background. But so on Thursday, we'll come back to this equation, and what we're going to do is apply E. We're going to change E here to 1/2 mv squared, the kinetic energy. And then we're going to look at some mathematics in order to convert this equation of kinetic energy and temperature into an equation that allows us to describe the box of gas perfectly. Okay, so this is just some background. We'll talk more about this kind of idea of statistics and probability on Thursday. Okay, that's all I have for you today. I'll see you guys Thursday. Homework's out. The LAs have solutions for those problems, so if you guys have any issues, go to them. They'll be more than happy to help you. Otherwise, have a lovely day. Oh, and this will be up on YouTube in about half an hour.